As promised, we're back, right? So this is actually, we're gonna do something evil here. So this is lecture 5 on game theory and vaccination, and we are now going to resume where we last paused. And this is exactly where we were when, as promised, we are resuming exactly where we were talking. So uh, when one writes this vertical bar and this little thingy on the bottom of that bar, that means evaluate expression, right? Evaluate expression. So this would be basically as a function of p, we evaluate that at 0. This would be 1 minus 1 over this quantity r0 times 1 minus 0, and we can see that this is equal to 1 minus 1 over r0. Okay, that's basically what we meant there last. If the vaccine is perceived to be sufficiently risky, um, then um, the relative risk exceeds the probability of becoming infected when the vaccination level is 0. Nobody really is vaccinating. Then the Nash equilibrium in that case is to never vaccinate. Okay, and so this is our first derivation of we're going to use capital letters with this star or asterisk here to denote equilibrium. So this is an extreme scenario in which the Nash equilibrium is to no, like, zero vaccination, neglect vaccination, completely ignore vaccination. And so the vaccination, the level of protection in the population would be 0. So if you think of evaluating this expression here at 0, basically nobody, there are no newborns in the original model, there are no newborns going to the R compartment. Okay, but going back to this, let's now examine a condition for the scenario in which we have a mixed Nash equilibrium. Okay, so um, pi 0, as we had worked out here in um, we just work out the expression for this pi sub 0 is 1 minus 1 over r0. So if we say that we're considering a scenario in which we consider a scenario in which, okay, so maybe I should point out that before we continue, the previous case here, the previous case for which we have an equilibrium with that neglects vaccination is under the condition that the relative risk exceeds the probability of infection when no one is vaccinated. Okay. Now we consider another scenario. What if that relative risk is actually less than that probability of infection? Okay, which is this scenario. And so we are trying to write a condition. What if R is strictly less than this difference, 1 minus 1 over R naught? Okay. Um, so this double arrow, which you may be familiar with this double arrow means if and only if. So we have the condition R, relative risk less than probability of infection with 0 coverage. If and only if, and what's happening here is think of think of um, swapping this inequality, this little r, with this fraction 1 over r0, right? If you send that 1 over r0 to the left side of this inequality and now send this little guy to the right side, then you end up with this expression here. Okay, so relative risk less than probability of infection at 0 coverage if and only if 1 over r0 is the lower bound of the difference 1 minus r. Okay, and that is equivalent. So what did I do next? I basically take this denominator or you can think of multiplying in both sides of this inequality by R naught, and that gives you this expression here. Okay, that gives you this expression. So a condition on the scenario of mixed equilibrium or mixed Nash equilibrium, condition would be that R0 times quantity 1 minus R, where R is the relative risk, that exceeds 1. Okay, that is exceeding 1. So now to compute the value of the mix Nash equilibrium, which we are going to still denote here with that notation with a star, P asterisk or P star, what we do is that we solve this equation. We set the relative risk equal to the probability exactly at that coverage P star. Okay, we say R equals pi sub P star, and what we do is we solve this equation for P star. So let's remember what that expression pi is. So that expression is equal to 1 minus 1 over R0 multiplying quantity 1 minus P star. And what follows is we have to do a little bit of algebra here, and there is a number of ways in which this will work out. So I'm going to continue this um, equation we're solving, right? So remember, we have this equation, R equals that, and what we want to do there is we want to solve this equation for P star. Okay, so um, let me continue writing here. So we have what I'm going to do is I'm going to swap R. I'm going to send R to the right side. I'm going to send this fraction to the left side. So I'm going to write 1 over R0 times 1 minus P star, and that is equal to 1 minus R. Okay, you can solve this in many different ways. This is a fraction here, and you may do the math here and not exactly the same steps that I use, but that's fine. We will both um, obtain the same equation. Now I can multiply this equation by R0 in both sides, and that would give me 1 on the left side, 1 minus 1 over 1 minus P star, and here I have R0 multiplying 1 minus R. Okay, and the next thing I can do is, so I start with this equation, and that implies, this arrow means implies, that implies that expression, this implies this expression. The next thing is I can take the multiplicative inverse, or I can raise to the -1 as an exponent on both sides of this equation. So I have 1 minus P star equals to 1 over R0 times 1 minus R. Okay, so from the previous expression, that implies this, and then I can just swap this P star, can move the P star to the right and this to the left. So this is going to give me an expression 1 minus 1 over R0, 1 minus R, equals P star. So this means that we have obtained here an expression for P star, right? So that expression for P star is precisely what we were going after. That would be, excuse me, the expression for the convergently stable Nash equilibrium. And you can see how that expression is holding for the scenario in which that's a non-trivial Nash equilibrium, right? So we have two types of Nash equilibrium. One, if I'm kind of running out of space here, so we had the first type, of Nash equilibrium, let's say R exceeding pi sub 0, and that gave us the trivial equilibrium, which was p star equals 0. And then now we have this scenario in which R is less than the probability that there is no vaccination, and that gives us this expression for this Nash equilibrium. Okay, and this concludes our lecture number 5 on game theory and vaccination.